Participants, our third expert talk is on hybrid graphene hexagonal boron nitrate materials and its applications. First of all, Dr. Rodrigo sir, have you joined in the Google Meet or not?
Yes, I'm here.
Good afternoon, sir.
Good afternoon.
So before starting off our Rodrigo sir's expert talk, I would like to give a brief introduction about him. He is currently an adjunct professor at University Federal Fluminense Advanced Campus in Redonda. He completed postdoctoral fellowships 4 times, 2 times from Brazil, Universidade Federal, and 3rd time from NTU USA, and in 4th time he completed his postdoctoral from Uppsala University, Sweden. He did PhD at Universidade de São Paulo. His research field is in condensed matter physics, with emphasis on first principle calculations using density functional theory. He is working on nanostructured materials, its properties such as electronics, mechanics, electronic transport, thermal power, among others. He is also interested in classical mechanics and quantum molecular dynamics qmmm methods. During the first time in 2013, when we organized an international workshop in our campus, he was one of the resource person along with Professor Ravin Pandey sir. And at that time, he was a postdoctoral fellowship fellow in under the Professor Ravin Pandey. So at that time, we learned a lot from him. So thank you, Rodrigo sir. Since then and right now, we have progressed a lot. At that time, we had no any research paper belonging to the dense DFT, and right now, only in this year, we have published 5 research papers based on DFT. Only is in this year, 2020. So you became one of inspirational resource along with Professor Ravin Pandey sir. So thank you a lot, sir, and you managed time according to our Indian time. And on behalf of the organizing committee, AICTE, I request you to please proceed for your kind invited talk. Rodrigo sir, please proceed for invited talk.
Okay, everyone can hear me? It's okay?
Right, sir.
Okay. Okay. Thank you for the introduction. I'm very happy to be here again virtually. Today I'm talking about hybrid graphene HVN materials and its applications. As Keshav says, I was in the first conference in few years ago, I think 7 years ago, and I'm here in this picture. Oh, I am here. You can see that a lot of guys here. Anurag, Keshav, Professor Ravi. Was a very, very nice time there, and I learned a lot, and I can give you some experience of the simulation that time. I spent a very nice time there. Maybe one day I can come back for a regular conference. But let's just say a few things about me. We are far away. I am in Brazil now, and we have the African in between. Here is Bilai, and here is Brazil. Brazil is like India, is a big country, and I am in the Rio de Janeiro state. here is the advanced campus where I work, okay? And this building is the physics building, and we have this computational physics undergraduate course. This university is a very big university. There is almost 50,000 students in this university. And here in my city, they have the engineering school and this new campus since 2010. This is the building that I work. I have some similarities between my city and Bilai. When I visited Bilai, I was surprised because it's similar my city. Here in Bilai, we have this siderurgy industry. In my city, is the same. It's similar. We are friends, and we have it very similar between these two cities. It's a technological city, and because we have this and many universities. Okay, but we are here to talking about materials modeling. Let's start talk about modeling. First of all, when we start a simulation, we should have some materials, choose some materials, and we need to choose some question about them. This is the first issue. And for each kind of material, each kind of problem, what we need tools. For example, if I'm interested in some material, and this material, I have electrons, I can't use classical molecular dynamics because in this model, we don't have electrons. This is important issue, okay? You have a model, you have a material, you have a question. You have these three pillars. Okay, here, if you have some continue this material, we have this material, these bricks. We can have different bricks made by AVS or green clay superior, AVI or green clay inferior, or kaolin. These three different bricks can have different composition or of different composition in this material, and this different composition give different properties. This is the main issue that I can say for everyone here today. Okay, but in this talk today, I will talk about graphene and HBN, these two 2D materials. And the first question that I can address is, are these materials stable? The second question is, what are their electronic properties? Okay, here is the band structure for graphene, and they have this crossing at the Fermi level. Okay, and this cross is given by pz orbitals. Okay, and for hexagonal boron nitride, we have a band gap about 4.6 eV. Graphene semi-metal, HBN isolator. Okay, the question is it possible we mix these two materials and control its properties? This is the issue here. Okay, and before answer this question, I will show some experimental evidences for the hybrid material. Here is the science paper, and they have this graphene, okay, and they have the etching process, and they start grow HBN in this bouldering, and they form this hybrid graphene HBN. This is the TEM images, and the STM, you can see these two interfaces, and BN and graphene. Okay, this is a theoretical study when these guys study different shapes, triangles and rectangles and so on. They had HBN and these shapes formed by graphene. There is different questions about that. For example, which termination we have, this is very important. And what's the form of this interface? Zigzags, armature, and so on. Okay. Okay. This is the last motivation. This is very nice paper, a little bit old. This is Ajahan paper. They have this etching process. They have this HBN. They have this etching process, and they form nanostripes. Okay, graphene nanostripes, and the control is impressive. They can draw a O made by HBN in a graphene template. You can see here in this picture this kind of control. Okay, and this is the DAM for HBN graphene, and so on. They have this kind of system. Okay, now we have our hybrid system. Okay, made by these guys. I will come back and in the deep understand about this using simulation. Okay, okay, but what this is. The last thing here, they made transport measurement. Okay, here they have graphene, HBN graphene, and they put some leads, okay, and calculate the probability of one electron comes from the left side and goes to the right side, okay, and they measure the IV curve. And we can see here, when we have the leads like this, we have some signal, okay? And the current flows through the graphene, okay? When we have the leads like this, okay, parallel to the roads, the current is 0, okay? Here we have the fundamental question that we address in the near future. Okay, we have some questions about this motivations. How is the minimal graphene width to have a metallic system? Is it possible use this system as a nanosensors or biosensor? I will show two applications. How about the interface? Which interface is more stable? If you expose this device to different gas or biomolecules, is it possible to identify these guys? Which method we should apply to model this system? This is the important question. We start for the model, okay? How can I solve this problem theoretically? This is important issue. First of all, we consider the full Hamiltonian when we consider the kinetic energy for the nuclei, the kinetic energy for the electrons, and nuclei interaction, this electron-electron interaction, and electron-nuclear interaction. We have this full Hamiltonian, okay? But for solve this problem, we just solve the Schrödinger's equation. We have this HPC equal EPC, okay? And you note the psi is in function of R and BR. The little r correspond to the electrons and the big R correspond to the nuclei. Okay, we learned in the quantum mechanics course that we can solve exactly this equation just for few problems. For example, free particle, harmonic oscillator, hydrogen atom. If you have 2 electrons, or 3 electrons, this equation doesn't have a exact solution. Okay, this is called many body problem. Okay, for example, if you consider for a system with 100 atoms of carbon in one graphene, the carbon has 6 electrons, okay, per ion, okay, and we have 600 electrons and 100 ions, okay. This is 700 body problems. This is impossible to solve, okay. Let's consider our system in the real life. What we have electrons and also nuclei moving, okay. But what you know, the mass for the nuclei is very big compared to the electron. Nuclei move much more slowly compared to the electrons. Okay. For example, if we have a R0 position for the nuclei, the electrons are automatically adapt for this position. If you move for R1, this electron instantaneously adapt for this new position, because we have different time scale between electrons and the nuclei. Okay. For this important point, we can model, we can fix the nuclei and just move the electrons. So the R0 is the nuclei fixed, and we can just solve the electronic problem. Before this talk, we have this tutorial, and we relax the structure of I don't know, H2, and we have, for example, when we have this SCF, the nuclei are fixed, we are solving the best position for this electrons. Okay, and after solve this electronic problem, you can also solve the dynamics. This is the Bohr-Oppenheimer molecular dynamics. Okay, it's also possible do this with CS or quantum espresso code. Okay, the dynamics of the nuclei and the electrons are decoupled. Okay, we can make this approximation. And for nanosystem, for example, we can see here the timing and the length. For example, 10 to the minus 9 is the size of our nanosystem. We have electronic regime, and the timing is 10 to the minus 15. And in this time scale, we can use density function theory. For mesoscopic and microscopic system, we can use statistical mechanics or thermodynamics or multiscaling process. Okay. What we have here, we back to the full Hamiltonian, and this is the full Hamiltonian that I told before, and this is the approximation. Now the electron is the electron mass is very small compared to the nuclei. This could be very small, and the Bohr-Oppenheimer approximation is my psi, the R big R, is split in electronic and the nuclear wave function. Note here we have a semicolon R semicolon R, and here we have R common R. What's the difference here for semicolon? In this case, the R is a parameter in the wave function. For each parameter, we can solve the electronic equation. But the electronic equation is this one: H electronic, psi electronic equal E psi. Okay, but this is, we have all electrons, and all electrons is 600 electrons. Is a huge problem. We can't solve this problem. You just you made the first approximation, and the system keeping without solution. Okay, how could you simplify this problem? Okay, in 1998, this guy Walter Kohn and Pope won the Nobel Prize, and this guy developed the density function theory. The basic idea is, for the Schrödinger equation, we have the wave function. In this wave function, we have 3n degrees of freedom. Is it possible we formulate a problem with the density? The density is very, very simple. It's more simple than the psi. The rho, we have 3 degrees of freedom, okay? The regular quantum mechanics, we have the potential, we have the wave function, the observables. This is the many-body problem. Density function theory, we have the density, we have the wave function, and we have the potential, okay? We have this correspondence between wave functions and densities. And the main issue here is the mapping of any body problem for one body problem. We have sum over all bodies, but we solve the one body problem, okay? And the density function theory is based on the theorems, two theorems, Hornberg-Kohn theorems, the external potential and as the total energy is unique functional of the electron density, or not just the total energy, but any observables we can write as a function of the density. The ground state energy can be obtained variationally. The density that minimizes the total energy is exactly ground state energy, the exact ground state density. If you have the ground state density, we have this minimum, okay? This is the equilibrium theory, okay? And Hornberg-Kohn just formulates these theorems, but they did not say how to proceed the calculations. And 1 year after that, Kohn and Chan proposed this mapping of many body problems for any one body problem. This is the DFT. The correlation potential can be minimized, the rho, okay? And this is the Kohn-Chan equation. This is monoelectronic Kohn-Chan equation. And this is one electron equation, and this equation we can solve, okay? Is it possible to solve in the computer? And these codes, Siesta, VASP, Quantum Espresso, solve this equation inside them, okay? This is important point. But in practice, what these programs make, they have a gas, okay, the density gas, and calculate the Kohn-Chan potential, okay, in function of the density, and solve the Kohn-Chan equation monoelectronic, okay. Monoelectronic, we solve for all electrons, okay, and after solve this equation, we can calculate the new density, okay, and this density we compare with the previous one. If this density is equal inside some criteria, okay, you go to the physical observables. If not, we come back to this self-consistent circle. This is SCF calculation when we have, for example, some calculation for a fixed nuclei. We solve this kind of self-consistent field. Okay. Just a diagram here. Compare the methods. Here we can have precision in this direction. Here we can have number of atoms. For example, ab initio methods is more expensive. We can spend more computational time, but have better precision. Okay. Side binding is a semi-empirical method. Is 3 orders of magnitude faster than DFT methods. Okay, but the precision is less than the ab initio method, but the number of atoms we can increase a lot. And empirical methods, as classical molecular dynamics, for example, we don't have electrons, okay, but we can go for a large number of atoms. For example, billions of atoms. Now we can use these GPUs and go to a very large system. Okay, and we can also combine these methods if it's necessary. Okay, today I will talking about few applications, and the methodology that I use here. I use this Siesta code, as everyone is learning this in this conference. I used VXC, GGA, and van der Waals corrections. I use pseudo-potential norm conserved, and for relaxation, I consider 0.01 eV per angstrom. My mesh cutoff, convergent mesh cutoff, is 300, and my K point is 3 by 3 by 1 for CG, and 1 by 1 by 150 for transport. This is an important point. For example, mesh cutoff is agreed in the real space. When you solve EDP computationally, we should discretize the space, and this mesh cutoff is a kind of discretization, and K point is also a discretization in K space. Okay, I think there is some exercise for the tutorial for converge these quantities. Before start some calculation, you should make some convergence tests for these two parameters. Okay, I would start talking about the hybrid device. Remember the experimental work. Now I start simulation with this nanorod. Okay, I have graphene, HBN graphene. I have the widget for graphene called W, and the widget for HBN called V. Okay, here is the band gap in function of the V widget. Okay, I fixed the W in 5, and I vary the V here. Okay, what we can note here, if I fix the graphene for this value, the gap is almost constant. Okay, I have different width for V, and the gap just decrease a little bit, but is keeping constant. Now I change. I fixed the V 90.5 angstrom, and I vary this W. Okay, and the width of W is in this axis, and the band gap here, and I have this decreasing of the band gap in function of the width. Okay, and what we can learn here, for 14 or 16 angstrom, we have this metallic system. Okay, we can control the electronic properties of this nanorod, just keeping some width for W and for V. Okay, and this is our system now. This system have 14 angstrom, and this is metallic one, and we can see here is the transmission. I have a electron here. What's the probability for this electron comes from here and reach this right side? This is the transmission. We can see two plateaus. We have these two plateaus close to 0, and we have this plateau with one channel here. Okay, what's if you see these atoms, we have this interface N1 and C1 is green, is red and green, and we have the second interface C2 and B1. You can see for this peak, the big contribution is black and blue. Black and blue, C2 and B1 is this interface. This interface is this. Oh, this interface B1 and C2, and this interface is the another one. Green and the red, we have the contribution for this interface. You can see for the transport, this plateau comes from N1 and C, and this plateau comes from C2 and B1. Okay, it's interesting because for one channel here we have the purple one, purple is the central carbon atoms. And in the center, we also have the carbon atoms contribution, okay? For these 2 points, I can project the transmission, okay, for minus 0.01. And this projection gives the local current. I don't have current here, okay? This is local current, means the probability, the projection of the transmittance. We can see here the projection for minus 0.1, and the current prefer this interface sites. And it's very, very small in the graphene side. You can see the wave function for this energy, okay, is concentrate in the interface. And this one is minus 0.5 is here, okay? And we can see here, we have one channel and dominated by carbon atoms, central carbon atoms. You can see the local current is basically on the central region, okay? And the wave function is spread in the central region, okay? Here's the density of charge, okay? Here is the carbon, the nitrogen. We can see the difference of charge here. We have a local dipole here, okay? And boron and carbon, you also have different of charge intensities. We have also a dipole moment in this region. Now I can make a pore in this system. When I make a pore in this system, what happens if these guys goes to zero, because the contribution is basically from the central atoms. And for these two plateaus, they have a decreasing, but we have some contribution. And when we project the current, the local current for minus 0.05 and 0.1, the current flows through this wire. This proportionally, we consider this carbon nanowire, and we have the current flow through there, okay? This is the wave function for the both system. And this is the work that I showed for them. There is two important possible application. We can use the last one, this, as a modulation system, when we can identify, for example, molecules through the resistance. And the first system could be a gas nanosensor system, okay? I will show these two applications. The first one, how can we read, this is modulation device, how can we read DNA, okay? Here is our device. I have my helper here, and they can put some magnify glass here or help us. And if the DNA pass through this device, and I can measure its conductance or resistance, okay? This is the idea. We should have some 2D materials or solid state materials and implement this electrical DNA reading or electrical DNA sequencing. And we have two basic issues for this kind of device. The translocation time should be small, and changes in the conductance and the resistance should be larger. Okay, this is the review about this field. We can have different setups for this. This is classical. We have this ionic current. This is the nanogap system. Okay, this is nanopore system like our proposed, and this is on top system. Okay, I have these possibilities, and this is our system that I showed before. This nanopore one is this one, okay? And we will show some DNA application. Here we have the DNA inside the pore, okay? And the black curve is the transmittance for the bare system or empty pore without molecule. And we can see difference for each molecule, we have different transmission, okay? How can we quantify the changes in the transmittance? We can have this sensitivity. Sensitivity, for example, is the changing in the resistance or changing in this conductance for this system. We can see here for each different molecule and the gate voltage for minus 0.4, we have these different sensitivities. This means I can identify each different nucleobase just by reading its resistance. And for plus 0.02, we also can identify electrically each nucleobase. Okay, but there is some interesting point here. If you consider, for example, A and T, the transmittance decreasing. Okay, for C, the transmittance increase compared to the bare system, and for G, for negative energy decrease, for positive energy increases. Okay, we did a model, simple model with 8F molecule, and we point the F through the wire here, and we put this 8 through the wire, and we consider two 8F molecules. Okay, and when I have F pointed to the wire, what happened? The transmittance decrease, like A and T. If I put the hydrogen through the wire, what happened? They open channels. What happened? Is like C. Okay? When I put the two molecules, they decrease for negative and increase a little bit because we have local dipole moment interaction between the molecule and the wire. Okay? And here the system try to cancel. Okay? But we have a small contribution. And the fact to have big or bigger or smaller transmittance is related to this dipole moment. Okay, here is the modulation for each nucleobase. We projected the local current. As we can see here, each system has different probability for the electron flows. Okay, this is the lower panel corresponds to the difference of charge density. We can see we have charge here and charge here in the close to the wire, and the probability, the current probability is smaller than this case. Okay. Okay, for this work, what we have, the single modulation device, we can, is it possible control the local current? We have this modulation system, single modulation device. We can identify or distinguish each nucleobase through the sensitivity. The high sensitivity makes hybrid single modulation device as a material for the third generation of DNA sequences. Okay, the last application today, I will show some gas sensor. Okay, and the idea is similar to the DNA sensor. We have the similar. I have the same setup here, but now I have this kind of material, two electrodes also connected to this multimeter. And this material could be nanotube, could be graphene or hybrid material. And we have some gas. This material has the resistance R, okay? And one gas goes through this material, and I can identify CO, okay? And this resistance, when this gas reaches this device, changes. This is the basic principle, okay? If you change the molecule, we have change in this difference. This is the sensitivity that I showed before, okay? And we should quantify, okay, these changes. There is these two basic issues. The translocation time should be small for you have a good sensor, and changes in the conductance and the resistance should be big for you identify different molecules and so on. Okay, now I consider the first system, this hybrid graphene HBM. When I have this HBM here and the graphene in between, and I have this CB, CN, these interfaces, and I have graphene nano sites, and I can have 1, 2, 3, 4, 5, 6. We have these positions, and we consider for gas NO, NO2, CO2, and NH3 in these 6 positions. Okay. Here is the binding energy or dispersion energy in these different positions. We can note CO2 and NH3. The adsorption energy is similar in all interface, CB interface, graphene, or CN interface. Okay, there is no preference to be attached. Okay, the gas. And for NO, we have the preference in CB interface. For NO2, we have a preference in CN interface. Okay, this is important because we can identify different gas in different interfaces. Okay, here is the most stable positions. Okay, for NO, we have 2 and 6 position. NO2, we have 2 CB, 6 CN, CO2, 1 CB, NH3, CN. This is the adsorption energy. Okay, this is big one, 2 EV, and this is the distance. The distance is smaller than van der Waals distance. They is considerable tight with the device. Okay, okay. This is the transmittance. The bare system is the black one. You can see here, but for NH3 and CO2, there is no difference here. There is no change in the transmittance. For NO, we can see, we can note the transmittance decrease for this plateau, okay, and for any O2 decrease for another one, okay. NO CB interface, NO2 CN interface. Here we consider the 2 most stable structures. We also can observe this changing in this transmittance, and we have also this difference of charge transfer, difference of charge density. That means we can see the charge redistribution into the system. We note for the most stable structures that we have this charge redistribution through the system, or the charge transfer between the device and the molecule. And this charge transfer is responsible for changes in this transmittance. Okay? Okay, let's understand what is happening now. Okay, this is the bare system without gas. We can see the interfaces CB, CN, and CB. We can see this plateaus is almost similar. Okay, this is responsible for this transmittance plateau, and the red one is the central atoms. Okay, when I have CB interface, and the gas are in the CB interface, what happens in the states decreasing compared to CN, because without gas is similar. With the gas, when they approximate to the CB interface, the state decrease. Okay. In another hand, we have this CN. If the gas goes close to the CN interface, these peaks decrease. Okay. For the gas NO, NO2, there is few states because we have less number of atoms compared to the system. But we have the states over there. We have this kind of hybridization states. Okay. Okay, now we calculate the sensitivity for two different gate voltage, because for positive gate 0.16 we can detect, for example, NO gas with 42%, okay, the sensitivity. And for positive gate we can identify the NO2 gas, 45%, okay. The conclusion of this third part is the hybrid device should be used as a gas sensor, okay? And CO2 and Na3 cannot be detected in the hybrid device. It's very difficult to detect these two molecules in this device. And this device is selecting the NOx gas, NO and NO2, through the interfaces. Each interface could detect each gas. Okay. For more details about this work, we have this paper published last year. I have some collaborators I told after that, and we have this paper for the DNA sequence. Okay. These are my collaborators. I would like to thank my collaborators. Vanderlan Scopel is from Brazil. Fábio Arthur, both professors here in Brazil. Ralph Scheincher is my collaborator in Sweden, was my postdoc advisor. In Germany, I have this researcher, Maria Fita and Jens Hirton. And the USA, I have the Ganesh Shivahama, is an Indian guy, my friend, and we have this kind of collaboration. And I also would like acknowledge the agency CAPS, CNPq, and FAPERG with these grant numbers. Thank you very much for your attention. I'm open for questions. Hello?
Participants, please raise any kind of query.
Good evening, sir.
Yes.
Please.
Hello. Am I audible, sir?
Hello.
Yes, sir. Can you enlighten us with van der Waals correction in siesta? More about van der Waals correction in siesta, using van der Waals correction in siesta.
For using van der Waals correction in siesta, you should have different pseudo potential. You can, for example, you can download from the website, the siesta website, the input file for generate this pseudo potential. After that, you can use in this atom program and change. You can change the approximation, and you can use different van der Waals corrections. You have D1, D2, and another approximation there. And but for using this, you should use the Siesta 4.02 or newer. Okay, is it possible?
So we can't use the already given one, no, sir? Like there is functional given van der Waals VDW. It's already given in the manual. But do we have to generate our own potential when we perform calculation?
You can repeat the question?
Sir, in Siesta manual, there is already given van der Waals. Yeah, but can we?
Okay.
Is it more appropriate to generate our own pseudo potential?
In the manual, we have this approximation, but you should have the pseudo potential, and you need to generate this pseudo potential. This is the point. You understand?
Oh, okay,
For
sir.
using
Thank
the
you very much, sir.
manual,
Yes, sir.
van der Waals corrections, you should
Oh,
have this VW or VL pseudo potential
yes,
with this flavor.
yes, sir.
Okay, it's not complicated to generate. Um, if you have some system, I have some pseudo here. I have CMP. If you want, I can send to you. But there is
Yes,
a
sir.
recipe to make this. It's not too complicated. I can send to Mohan or other people and can give you this pseudo potential for
So we
everyone.
can access from them. Oh,
Okay.
thank you very much, sir.
Yes. Any further question? No further question?
Hello.
Hello.
Sir,
Hello.
I have one question. For making a biosensor or sensors, we consider that up to this concentration, this sensor will did not detect this gas. If we assume that nitrogen oxide or nitric oxide gases are also present in atmosphere, means up to which concentration experimental people are think about that they make a sensor in such a way that they can detect up to this concentration, otherwise it will don't detect. Means how theoretically we can improve these results, because we only take here only single molecule.
Yes, this is only a single molecule, but our system is periodic. It's not a small concentration. This is high concentration. Your question is very good. We could increase the concentration with the calculation, but we have a limitation in the computational. Okay, and we have more sophisticated methods that we can have this disorder system. Okay, I have some work in this direction, but the problem is we should go to 60,000 atoms and change this concentration with disorder. And this is very, very heavy to run, okay? But regarding the experimentally, for example, depends of the system, they have this part per billion atom in these sensors. Each sensor have this, but you should increase the system for have this kind of concentration. I agree with you. It's an important point, but we should have this. This is a model. The model we can start with the model and have answers, simple answers, okay, for the systems. Of course, we should have improve these models, okay, and go to the disorder systems and different concentrations. I'm working in another sensor project now, and we are varying the concentration to see some tendency. This is also important. Okay, good question.
Hello. Hello.
Hello.
Sir, I have one question regarding that gas sensor. How to distinguish between the chemical absorption and phase absorption based on
Sorry, I think that I can't hear you. Can you repeat, please?
I am telling that how to distinguish between chemi-absorb and physio-absorb system based on absorption energy and optimal distance.
This is a good question also. We have two issues. Translocation times means how long the gas will stay into the device, okay? And the adsorption energy is proportional to this translocation time. If you have high adsorption energy, the gas will stay forever in the device, okay? And we should have a small binding energy and high sensitivity for detect the gas. We can play with these two But when you have a small binding energy, in general, the sensitivity decrease also, and we can have the best of these two quantities for detect. We can detect for the timing that the gas stay there or the molecule, and we can detect it through the changes in the resistance.
Okay. And another thing is, sir, that how you have applied the gate here. You have seen that based on gate voltage, you are calculating that selectivity, sensitivity. So
Okay,
how you?
there is two ways to include the gate. No? For the newest version of Siesta, we have a multi-probe, multi-electrodes. We can also include right and left and a gate above or below. We can put this extra electrodes, or in this simple model, we just tune the Fermi level for a specific energy. If you consider that we have a rigid moving of the states, I consider the second one, okay? Because it's very, very tough, this gate voltage calculation.
Okay. And another thing is, sir, that I have done a calculation for transistor calculation for, and I have found that in the transmission spectra there are some peaks which are having a step-like behavior. Also, some uh, uh, some along with some small peaks around that sharp peak. So, what is the meaning of that kind of peaks? Could you please give me some?
For this peaks, you should.
In general, we know that the peak should be in transmission spectra. The peak should be step function behavior. Peak shows step function behavior. But I have
Yes.
found some system in which, apart from the step function behavior, there are some other small peaks having discrete nature. So, what is the reason behind, or what is the physical significance of that?
This for you investigate these peaks, you should go to the dense of states, project the
Yes,
states at
yes,
that energy, okay? As I showed before, you project there and try to see which atoms or which orbitals are participating there. Is it possible make some correlation between transmission and also the peaks? This is the first one. The second one is we can also show this wave functions. We can, for a specific energy, we can plot the wave function as I showed before. The wave function is different the charge density, okay? We can have the information for a specific energy. Charge density, we have the information for Hall density, okay? Hall energy range. And with this information, we can say about this resonances and another point.
okay, okay, sir. Thank you.
Any further question? Okay, thank you, sir. Thanks a
Okay.
lot for extra time and shared your valuable time, and as well as gave a fine lecture
I'm
and
very happy to
manage your
speak.
time with our Indian time at early morning. Thank you, sir. Thank you a lot.
Okay, and very happy to be here again, but virtually, but again. And I hope the students and everyone can have a good conference, okay? And if they have some question or some point, please write me and I can help you, okay? Bye-bye and see you.
Good day, sir. Good day. Meet you again, sir.
Okay, bye-bye.
Bye, bye, sir.